Do you have any doubts from the last class? 1 minute. Give me a minute, please. So in the last class, we talk about the process design kit PDK. What is the process design kit PDK? Then we talk about some analogies. Then what are the categories where we have discussed about the PDKs? What are the device models, design rule files, standard cell libraries, then technology files. Then we talk about the LVS and the PEX decks, then GDS2 and the documentation process. Then we saw the importance of PDK in our VLSI design flow, and in each part of the flow where like PDK do what. For example, in logic synthesis, the PDK's work is to provide us the standard cell libraries through .lib file and the .lef file. When you go to the floor planning, there the technology files are the DEF and LEF file. And in the placement, we use the timing models and the cells of the LEF files. Similarly, in the clock tree synthesis, we use the RC models, right? And in the routing part, we are taking DRC checks and the metal layers. Okay. And during the signing rules, we are checking the rule decks of the PDK, and accordingly, we are deciding what to do. Okay, so that was from the previous class. Then we discussed different components of PDK and how the particular hierarchy of files are designed in our PDK directory. Okay,
You're
so
writing something.
no, I'm not writing
Oh,
something. I was just briefing the last class. Now I'm writing, so you can see. Okay, okay. Now I told you like we have different foundries, right? So these foundries develop PDKs. Okay, and these developed PDKs are provided to the IC designer. Now IC designer use these PDKs to give a standard format to Foundry so that they can work on that and provide the correct file to them. Okay. Now I told you like there are not much foundries available, right? So there are only some 5, 6 foundries are available. For example, Intel, TSMC, Samsung. Okay, global foundries. Okay, and yeah, like these are some of the foundries. Okay, so they have their own PDKs as well. So if you are using PDKs of any one company, then that PDK is cannot be used to design like to give the GDS2 file to other companies. Okay, so each company has their own, like each technology node or each technology file have their own PDKs corresponding to their company. Okay, so they take that PDK. Okay, so if you see, so most of the PDKs are provided by these companies like Intel, TSMC, and Samsung and Global Foundries. So TSMC is the very well-known like foundry company, that is Taiwan Semiconductor Manufacturing Company. Okay, now they have their own lead node as well. It means like if you see the TSMC is right now working on the 2 nanometer and the below 2 nanometer as well. Global Foundries are doing for 12 nanometer. Then Intel is doing some in angstrom, then Samsung is doing in some nanometer. So accordingly, they are using different technologies, and similarly, they will provide the different EDA partners as well. Okay, EDA partners means these files can be like these PDKs. Okay, the IC designer will be using these PDKs, so they will be running that PDKs into some tools. Okay, some EDA tools. Okay, so those tools should also support that PDK. So if you see that PDK you got from the TSMC, Intel, and Samsung, all these PDK should also support the tool. Okay, so if you see most of the EDA tools are mainly the Cadence and the Synopsys. So EDA tools, most of the EDA tools are from the Cadence and the Synopsys. So these are the two bigger companies which provide. Okay, so these two companies provide support to each of these PDKs or most of the PDKs. Okay, which we are using in the designing process. Okay, so that is one more thing. Now we'll do the deep dive into the PDK fundamentals. Okay, so first we'll see the device models in PDK. Device models in PDK. Okay, now we'll see what are these device models. So these device models are basically the mathematical representation of semiconductor devices. So we are representing these semiconductor devices as a mathematical model through these device models in RPDK. Okay. Now, what do they do is they allow some spice simulators. They allow some, okay, what happens to that? They allow some spice simulators. Okay. These spice simulators are used to predict. To predict what? To predict the electrical behavior of your circuit. Behavior of circuit, and that too without any physical fabrication. It means you have not did the physical fabrication of that device, but still you can exactly mimic the same behavior in your spice sim. Okay, so those are the spice simulators and we model our device models in the RPD case. Okay, now first one come among them is the MOSFET. Okay, now you know MOSFET. Now you know MOSFET. What is MOSFET? That is metal oxide semiconductor field effect transistor, right? That is the basic. Okay. Now this MOSFET is the fundamental device we know. So every PDK will have that MOSFET because this is the fundamental device. This is the fundamental device. Hmm. So if you see the either in analog or in digital, you will see everything revolves around the MOSFET. In analog and digital, everything revolves around the MOSFET. Without MOSFET, there is nothing. MOSFET is the basic building block, right? So if you see the physical structure of it has the gate, okay, and after that we have gate oxide, we have source, we have channel, we have drain, okay, we have and similarly in the substrate side we have P-well, N-well and whatnot. Okay, so these things are constituted and made the MOSFET, right? Right, right. And similarly, the operating regions are there for the MOSFET. Okay, so depending on the threshold voltage or the VGS voltage and the VDS voltage, we can determine the MOSFET is in the cutoff region or in the linear region or in the saturation region or in some sub-threshold region. Okay, so these key parameters of the MOSFET, that is VTH. Okay, what is that TOX of the MOSFET? Okay, what will be the saturation voltage? What will be the CGSO, what will the gate to drain, source capacitance, and all these values. So all these values of these MOSFET models, which are already present in your PDKs, are stored. Okay. Now, this is about the one MOSFET device, right? Now, similarly, we have the different flavors of MOSFET devices in our PDK. So different flavors are there. Okay. So we can say MOSFET flavors in PDK. There are different MOSFET flavors in PDK. Okay, what can be these? So we have high VT. We have a transistor that has the high voltage, high threshold voltage. Okay, we have the SVT that has some standard threshold voltage. We have LVT that has some low threshold voltage. Okay, okay. So depending on what or where your MOSFET is going to use, you can select that particular type of the transistor or the MOSFET. Okay, so this PDK has all things like it has the device models of MOSFET. Then in MOSFET also it has the different flavors, and what flavor you want to use depending on your design, you will use that. Now you say high VT. High VT is basically the high threshold voltage that is slow, but it is high power saving, but it saves a lot of power. Okay, similarly, if you talk about the SVT that is standardized, so that is the balance. It don't have that much trade-offs. But when you because it's SVT at some mean value. Okay. So if you go, this is VT. If you increase your VT, go here, and if you decrease the VT, go here, then this will be the SVT, this will be the HVT, and this will be the LVT. Now this is the balance condition. Okay. Now if you increase the VT, if you go this side, okay, that time we are saying this MOSFET will be of high power saving. But this is at the cost of slow. This MOSFET will be slow. This The transition speed of that MOSFET will be slow. But similarly, we have LVT. Okay, so that is again what? That is for the high performance because it has the high speed. Okay, but it will be having more leakage power. So everything will come up with a trade-off. So all those models are already present in RPDK. Okay, now this is about the device MOSFET models in RPDK. Okay, there is one question, sir. Would every different real physical parameters would be defined and considered in the PDKs of MOSFET? Okay, every parameter or every parameters are already defined in the PDK. When we go to the tool and see these PDK, then we'll see each of the parameters are already defined, but like depending on the model you are seeing. Okay, so if you are seeing the HVD MOSFET, you will see it has all the electrical parameters. Okay, so that MOSFET will get that high VT. Okay, similarly for the SVT and LVT as well. Okay, so it will has all the electrical parameters, physical parameter, dimensions, what will be the width, and everything is there. Okay, so after MOSFET we have the resistance. Okay, now resistance or the resistors I can say in PDK are not that ideal because these are not just simple resistance. Okay, this will because we are talking about the like technology depth of 1 nanometer, 2 nanometer, 3 nanometer. Okay, and there it will have lot of effects from the temperature, from the parasitic capacitance, and it will be dependent on the voltage as well. So all these things need to be included in that resistance. It should not be that ideal that we are using in our like electrical devices in our homes, like 1K, 2K. It's not that way. Okay, it will include all the temperature coefficient, parasitic capacitance, and the voltage dependency. We need to include all these things to make these resistance models. Okay, now we will see what type of resistance are there in our device or are in PDK. So we have poly resistors. Okay, so we have what? We have poly resistor. Okay, we have N-well resistor. We have P plus diffusion resistor. We have N plus diffusion resistor. Okay, we have metal resistors. Okay, so similarly, we have different other types of resistors as well. So now, if you see, if you are using some, let's say, silicated or some poly resistor, it means that has the resistance of some tens of ohms or 20s of ohms. Okay, if you are using some N-well type of resistor, it has some 10 ohms. N-well type of resistor will have the resistance of around 400 ohms or maybe to 1K or 2K. Okay, now if you go into the P plus diffusion, that has some 100 to 200 of ohm resistors. Okay, so similarly, different types of resistor models has different type of resistance. So how much resistance you want to apply or use, depending on you will select all the resistors. Okay, now these resistance are also depends on the length. You know, resistance rho always depends, like this resistance always depends on the length and volume, right? Or the width or the dimensions of the device, right? So similarly, you need to and you need to take the effect of that as well. So, let's say your resistance is some research and it should include the change in length because let's say your device is working on some like at a high temperature. Okay, that time what happens is since these 1 nanometer 2 nanometer wires are very thin. Okay, so due to that increase in the temperature, what happens is some of the part of your wire, so some of the metal from your wire may shift towards it towards the corner side or somewhere side. So what happens is that side the temperature, that width might change. Okay, due to the change in that width, your resistance might change. So you need to take the effect of that as well. Okay, similarly you need to take the effect of your temperature as well. Similarly, like if it is temperature dependent, it should be something like that. Temperature coefficient alpha T1 and something. other parameters might as well. Okay, so again, I'm taking these as the reference resistance. Okay, so depending on this reference resistance and the reference temperature, you need to model this, and all these modelings is already present in your PDK. Okay. Similarly, there comes for the capacitors. Then capacitors are very, very, very important because this is used, this capacitor, this is used in the filtering, it is used in bypassing, like it used as a charge storage. Okay. So this capacitor has a whole lot of usage. Okay, now there are different types of capacitors in RPDK. So there can be metal insulator, there can be metal oxide or metal to metal, then high precision, then PN junction capacitance, poly to poly capacitors. So there can be that type of capacitors, and all these capacitors are present in the PDKs. Because whatever you want to use, you need to take it from PDK only. It should not be, you should not be creating, or you might be creating your own, but that will not be then matching with the foundries. Right? So that is the one thing. Now again, depending on the what type of capacitors you are using, okay. So the capacitor value, for example, if you see poly to poly capacitor that has some 1 femtofarad of values. Okay, if you want to increase, then you if you use the most capacitor, then in that case like your capacitor might increase to 10 femtofarad and more. Okay, so those capacitor model parameter like oxide capacitance per unit area, then flat band voltage, oxide thickness, what is the voltage coefficient, all these values, all these parameters are defined in the PDKs. Okay, then this capacitor will also depend on the temperature and the voltage and change in the voltage, everything. So we need to take account of all those things as well. Right? Now comes the main important thing. So this is the main resistance capacitance and the device MOSFET model. Now comes the main thing, that is a SPICE model. SPICE models. What do you mean by the SPICE model? So the abbreviation SPICE stands for the simulation program with integrated circuits emphasis. So it is simulation program with integrated circuit emphasis. That is your SPICE. Okay. Now, this spice is developed by the UC Berkeley. Okay. Then one more question from Nikunj. He's asking, sir, at that tiny level of circuit, would capacitance affect the circuit? Yes, capacitance is a big part. Capacitance affect the circuit, even though you are not like putting some capacitance there, but the capacitance will come up there. Capacitance is a like it's not that it seems you easy because you haven't used that at the fabrication level, but when it come up that level, it is it yes, it affects the circuit, and it will affect the circuit because capacitance is a very important aspect of your PDKs and your device circuit. And remember one thing, capacitance are big in size, they are never in small in size. Okay. So where are we? Okay, do you have any doubt till now before this spice models? If you have any doubt, you can ask me. If you have any doubt, you can ask me. I'm giving you a minute, and after that, I'll start the spice models. No doubts. Good. Now we are talking about this SPICE models. So what is SPICE? SPICE is this simulation program with integrated circuit emphasis. Okay, so this spice programs are developed by the UC Berkeley. Okay, and this is the universal language of circuit simulation. So whatever circuit simulation you are doing in the analog, this is the universal language. Universal language of circuit simulation. Okay, now you can see your spice models. Okay, so you always remember your circuit netlist will be in this form. Circuit netlist will be in form .sp, .spi, .cdl, something like that. Okay, and you provide the spice model to this. Spice models to this. Okay, and your spice model should be of type this .spi, .lib, .mode, something like that. Okay, and then you provide this to the spice simulators. And these spice simulator then generate you the waveforms. And these waveforms are of type that can be voltage to time, current to time, AC response. They can also show you the noise and everything. Okay. Now you talk about the spice simulators. Now we talk about the spice simulators. The popular spice simulators are from the Cadence and the Synopsys. So Cadence provide this spectre. Cadence provide this spectre. So that is the spice simulator. Similarly, Synopsys provide this H spice. Okay. Then there is one open source which you guys might be using in your current schooling, like your college schooling. Okay, NG spice, which is mostly used by everyone, right? In your BTech or MTech. Okay. So that NG spice is the open source spice simulator. So you guys might be using this. Okay. So NG spice is there. Now you will say how your spice model file look like. How your spice model file structure look like. Okay, let me search if I have that spice model file. Just give me a minute if I can open you. Let me search. I forget if I have, but let me search. Give me a minute. Share the screen so that you guys can see. Anyone can confirm, is my screen visible? I will come
Yes,
to. Okay, okay. This is the, I think, ngSpice manual. Okay, let me open it. Huh? Give me a minute, then I'll tell you. Mhm. I'm searching for that file. Don't, okay, that might be not the simulator available in this laptop. Okay, I don't have that ngSpice installed in my system. So for now, let's don't go into this. Okay, so if you see, this is the type of this is how your like that spicing look like. So if you see, let's say I want to design an inverter. Okay, so how do I define the a MOSFET, let's say. So how I'm doing is this MP1 is basically a P-type MOSFET. Okay, so here see here this MP1 output input supply. So it has some fashion. We'll come to the reference module. Okay, there we'll see. Okay, it has some reference module, and accordingly, I'm deciding some length to this, width to this. Then this is area of drain, area of source. Then this is the PD, PS, and everything. And similarly for the PN1. Okay, and now you are this, like you are also doing the VDD and supply voltage. Like if it is DC, how much it is? It is 3.3. What is this zero? So all these things are indicated in your spice folder or your in the edge spice. We'll come to that. Okay. Okay. Now how you are connecting? You are connecting that circuit with the, like your DUT and inverter. You are writing the load capacitance. What are you including? Dot include model. So I was searching for this model file. I'm not able to find it right now because I have to see in my laptop where it was. I missed it somewhere, or I have to see. I'm searching for that model file. So if you see, these are the uh, so these are the circuit files. So we are inputting that model here. Okay. So since I've deleted that ng spice, so that's why it's not there, because I've copied that from my previous laptop to this laptop. So that might, okay, just forget about that. But this is the way it has written. Okay, something like this. Okay. Then we include that model because once you are using these values, you have defined the length, W, ED, AS, and all those things on your own. Right. Okay. But how these things are going to be taken by your device? Okay. So for that, you need to import the modules. Import the models. Okay, that model has all the information to create this particular MOSFET of length, this, width, this, area, this, and AS this. Okay, so similarly, that model use these parameter values to generate the circuit for you. Okay, and it will plot the DUT out and everything for you. Okay, now if you see the reference model, okay, let me show you that as well. So this is how your MOSFET will actually look like when it is like it is when you do the layout of that thing and when you see that at the foundry level. This the middle one is the gate. Okay, the side one is the drain and this side is the source. Okay. Okay. This file will have that thing. So it has all these things. I can share that this file with you. So here you can search for what type of analysis you want to do using the NGSpice. So all type of analysis are supported through the NGSpice. And how do you do is, so all these, now see, these are the mathematical models. Okay, so you need to take those values and accordingly the model file will take those values to create the model for you. Hmm. So it is telling us how do we create it. See, if you want to create some model device model, then you need to give the names and how do you define this. If it is an NPN, what will be the values of these things and what this BF indicate, IS indicate, all is provided in this file. Okay, and how you are going to use, for example, you are creating a resistance. Okay, now this resistance will has this value 10k, and you are, and these 1 2 these are the, like def what should I say, these are the nodes of the circuit. So accordingly, depending on the node of the circuit, so let's say I have decided this. Let's say I have this type of resistance, or let me take this MOSFET. Okay, and this this is ground something, and there is one capacitance and this is ground. Okay, something like that. Okay, so what you will do is you will give names to each ports. This is one, this is two, this is three, this is four. Okay, and this point is also one only because we are connected with the same wire. Okay, now when you are, let's say, when you are deciding this capacitor, so what you will say is this capacitor, like they had R1 1 to 10K. Similarly, this name is C1, 1 4, let's say 1 femtofarad. Okay, so similarly, you will do. Now, this means is this capacitance will be connected to node 1 and node 4. Similarly, you will write MOSFET NPN, let's say NPN. Okay, now it has similar fashion 1, 2, 3. So 1 is the this terminal, 2 is this gate terminal, 3 is the source terminal. Similarly, right? And then you write the other parameters as well. So there is some definition of writing this. Okay, so you need to take care of this. So when you return this type of thing, it will eventually convert into the circuit. So similarly, if you see here, not exactly here. Okay, we'll come to that in the future sessions. Maybe. Here if you see, okay, here instead of 1, 2, 3, I have given the name as output A, joint A, okay, output B, joint B, then A bar, B bar, B, name of the terminals, right? So I've given this name. So that depends on the designer who is designing this thing. Okay, so depending on that thing, you will design the circuit, and the Spice tool will take that as that circuit and design the things for you. Okay. Now, this dot includes models.cir. That has all the information. Okay. So, and that has some parameters as well. So, you need to define that parameters as well. And what are these parameters? You need to take care of that. So, that is about the spice models. Okay. So, do you have any doubts? Do you guys have any doubt? Is my screen visible? So you can see this is some TSMC 28 nanometer NMOS model device. So here you can see dot models. What is the name of the device? NMOS SVT. Okay, so this type of, and how we are aliasing that name as NMOS. Okay, now what will be the level version of that device? Because after some time they keep on changing the your devices. Okay, so that version is still showing. Now what will be the threshold voltage parameters? So it has threshold voltage parameters of 0.3850. This is 0 by threshold voltage. Okay, K1, K2, K3, then DVT voltage. So these are the extra or the in-depth, the second order parameters of for the threshold voltage parameters. So those are already present in your spice file, in your model file. Okay, so this is the TSMC 28 nanometer NMOS model. So similarly, it has the mobility parameters, it has the velocity saturation values, it has the oxide and geometry, it has capacitance values of this type, and noise parameters of this type, temperature coefficient. So it has all these things. So this is just a NMOS device of SVT. Similarly, we have thousands of or millions of devices. Okay, so this model file have all those information, and SPICE models use these model files to create their circuitries. And we are using these model files only to decide the parameters of those values. And we are simply changing the WL and ADAS values only. All these parameters are fixed. Okay, so this is the kind of your PDKs have, kind of thing PDKs have. You understood it, right? You understood it, right? Okay. Yeah, good, good. Now, similarly, we talk about the spice model. Similarly, we have the parameter extraction process. Now, this parameter extraction process is basically PEX only, right? We talk about in the last class. Now, what does this process do? Is this parameter extraction process do is, so the parameter extraction process is basically fitting model parameters to measure silicon data. This is what fitting model parameters to measure silicon data. To measure silicon data. Correct? Correct. Now, how our extraction flow will start? It starts from the wafer fabrication. Okay. Now, after wafer fabrication, what do we have? We have the electrical measurements. We have the DC values. We have the capacitors. We have the AC like noise and frequency and temperature and whatnot. Then after that electrical measurements, we go for the data pre-processing. Okay, and we optimize everything. Then we use the spice model parameter and model validation to create the correct model generations, right? And these corners, okay, that should be in the TT, SS, FF, SF, and FS. So these are the corner model. These are the corner model generations. So on the slow side, fast size, slow fast size, fast slow side. So these parameters, like if one transistor becomes slow and other become fast, and if both the transistor become false, oh sorry, fast, then slow, fast, slow. So all these corner cases we need to check after we have fabricated, after we design our circuitry. So those things are also present in our device, are present in our PDK, right? Now the very compact models that are present in our PDK, the compact model I should say. Okay, so that is the BC models. BC. So these are the simplified physical based mathematical models, and these are used to calibrate to measurement data. Okay. So if you have any questions till now, do ask me. Any questions you can ask.
Yeah, you can.
Okay. So now comes the now since you are using these models. Okay. Now these models will be used to create the layout floor, like first floor plan, then other thing, then layout. Okay. So eventually we'll go towards layout. Right? Now, whatever model you have modeled through your spice models, okay, that should create a correct layout, right? There should be this model to layout correlation. What should be there? There should be that model to layout correlation. Model to layout correlation. And what is that? What is that? So basically, what do this model to layout correlation doing is it is basically ensuring us that our spice simulation matches with the actual silicon measurements. So what it is doing is it is ensures us that our spice spice simulation match actual silicon measurements. Okay. For that, what do they need to do is they need to account what? Account the layout dependent effects. So account for layout dependent effects. Now, why is this critical? If I ask you why that is critical, because when you are doing these things, when it is used in layout, it will go to the silicon. Silicon will come up after the foundry manufacture that after the passing of yield, everything it will come out in your hand. Now, now you can use that device. Let's say that chip is going to use in your mobile phone. Now, today you are here. Let's say today you are in let's say in Bangalore. Okay. The weather of Bangalore is pretty good. The temperature here is around somewhere around 20 to 24 degrees Celsius. Okay. Now you got some 2 weeks of holidays. You plan to visit, let's say, you plan to visit Kashmir. You went to Kashmir, taking that phone with you. Okay. Now after reaching Kashmir, you realize the temperature here is some 1 degree Celsius, 2 degrees Celsius, 3 degrees Celsius. Now, The same phone which was earlier working at the 20 degrees Celsius in Bangalore should also work there at the 2 degrees Celsius. Okay, it means temperature got reduced. Temperature got reduced. It means your circuitry should function at that temperature as well. Now, let's say one of your friend went to Rajasthan in some parts of Jaisalmer and Jodhpur, some part of Jaisalmer, let's say. Okay. Now their temperature is 45 degrees Celsius. It means temperature got increased too much. It's more than double, right? Okay. Now your circuitry should work at that temperature as well, right? So it means whatever models you are creating there, okay, those model to layout correlations should account all these big effects. It should take care of all these effects. It means you must have simulated all these effects at your like before your device went into the what you say fabrication. Because after fabrication, you cannot just go there and here. You do the temperature stress test and whatnot. Okay, so all these things, all these stress thing, and all you need to evaluate beforehand. And to evaluate all these things, your device should take care of all those things. Device model should have all those things to account all these things so that you can predetermine all these things. Because if you lack something, this will result into yield loss. And yield loss means your chip will not be passed to go in the market. It will be discardable. Right? So that is the main thing about the model to layout correlation. So you understood why we need that correlation so much, because that ensure our spice simulators match actual silicon measurements, and this account for the layout dependent effects. So these effects should be there in the layout, right? Right. Now what will be the correlation flow? What will be the correlation flow? What will be the correlation flow? So first step will be we have to design that test structure in the layout. We have to design test structure in the we have to design the test structure in layout. It means you need to take care of the isolated NMOS and array NMOS or the different combinations. Then you go for the fabrication at the silicon. Fabricate on silicon. Then you measure all the electrical parameters. Then we measure all electrical parameters. And then after measuring all these things, we pass all these parameters to the spice model. That's how we create geometric info to spice models. Okay, and that's how we got these parameters, right? This is the way. After that, we run the simulations. Run the simulation both in the layout in the device and the this thing in the simulator side and compare. Okay, after that, what do we do is we compare the simulation results with the actual silicon. Compare simulation versus silicon results. Ki, will the VTH error is coming up less than 2 milliwatt or what? There is one question. In this tool, we run fabrications in silicon step. See, fabrications is not something we run, right? Fabrication is when we got the final step like GDS2 file, we give that to the foundry, and foundry will create that into the chip. So that is the fabrication. Fabrication we don't run and we can't run, right? We do the simulations. We have the environment of simulation. We are exactly emulating the same like characteristics of the device, right? You got it. I didn't get your question because it is something like it is that might be a fundamental issues in your understanding. Because you are asking in which tool we run fabrication in silicon step. So we don't run fabrication. Fabrication is we do fabrication, and that is done by the foundries. And we can't we cannot design like we can design everything and cannot do the fabrication and get the chip because that will be super costly. That's why we are using tools to run the simulation and do these. That's why we had the PDKs so that we can get the actual behavior of the circuitry before going into the fabrication, so that we can determine what need to change and how. Okay, you understood, Abhijit? Abhijit, you got your answer, is it? Or you have some other questions, you can ask that as well. Yeah, thanks. Okay, okay, good, Abhijit. Okay, so where were we? We are saying then at the sixth step, we'll compare the simulation results with the silicon. Okay. After comparing, we realize that there might be some, like, let's say there can be some VTH error, threshold error, that can be less than 2 milliwatt. Okay. Some GM error that can be less than some 2%. So, okay, so we will take count of all this thing and will accordingly modify our model parameters. Right? Is this clear? Is it clear? If you have any doubts, you can ask me. Let me take out the directory structure for you guys. So let me show you the directories. So you can see my screen, right? Okay. So now here you can see. So our PDK is basically this type of, the PDK root directory will be in the tools PDK folder. You will see TSMC 28 nanometer version 1.3. Okay, the version means 1.3. 1.3 is the version. Okay, now in the doc folder, you will see the documentation about the design rules, spice models, PDK release notes, and the layer definition. Then in the model section, you will see Spectre. So since this PDK you can use in the synopsis or you can use that in the cadence as well, right? So if you are using that in the cadence tool, then they will be using this Spectre. And if you are using that into the what to say synopsis tool, then it will be using the HSpice. So in the Spectre only you can say there will be top level.scs file. So that is the master model include file. So that we always include in our CIR files. Okay. Similarly, it has the NMOS file, PMOS, resistance, capacitance, that's everything. This is just an example. This much of files are just an example. There are infinite number of files. Okay, similarly in the Spice Aldo is also a spice simulator only. Okay, now in the cells you will have the standard cells. Now in standard cells you will have the HVT type of cell. You can have the LVT type. Okay, you can have the SVT type. So for the example point of view, here they're like showing you this like the LVT and the only for the HVT. Now in HVT you have the GDS files, LEF files, and the LIF file. GDS folder will have the layout GDS2 file of that particular standard cell of HVT type. Okay. Then in the LEF file you will have the abstract layout LEF file. LIF file will have the timing library file of the at different corners, TT corner, SS corner, FF corner, FS corner, SF corner, something like that. Okay. Then in the CDL you have the spice netlist. Verilog you will have the functional model. Okay. And the viewer file will have the symbol views. So you also see those file in the symbol as well. Okay, because you will always not be able to see the device structure only. You will be using some symbols for that. So when you click on that symbol and go into that, then you will see the actual file. Okay. Similarly, it has the standard cells, IVT, IO cells, memory, and all these files, all these type of files, all these type of files are all present for the LVT, IO cells, and memory as well. Okay. Now you say for a single MOSFET, or let's say NMOS or PMOS or an inverter, okay, there will be this much of files. Similarly for NMOS, PMOS, AND gate, NAND gate, NOT gate, NOR gate, and whatnot, muxes, decoder, everything is already present in your PDK. So that many number of files will be there. Okay, now in the text file, you will see you will have the text file, display file, LEF file, map.txt file. Okay, something, all these files will be there. Then at the PVT is the process variation temperature. So you need to like maintain the decorum of your device at all the temperature, all the process changes, right? All the variations. So for that you have the PVT. So for that calibrate DRC. Now the DRC will have the DRC rule file, DRC.wave files. Okay. The LVS file, layout versus schematic, DRC is the design rule checks. Okay, PEX file, that is the post extraction. So that has the rule file. So all these rules files will tell you whether the particular device you have model is correctly meeting the requirements or not. So all these files are included in your PDK, right? Then in the cadence folder you can see the cds.lib, that is basically the library definition file. It has some virtuoso is a cadence tool. Okay, all these things are there. Similarly, in the synopsis folder, you can see the parasite. You can see the IC compiler too, that is the synopsis tool. Design compiler, that is a synopsis tool. So all the synopsis and cadence related setup files are there in their folders. Okay, then we have the scripts. We have the script to run the DRC. We have the scripts to run the LBS. Then we have the scripts to run the PEX. And similarly, we have the model check.py, right? So this is the structure of the, what do you say? What do you call it? The structure of the like directory structure of your PDK, top level directory structure, right? This is very important to understand these hierarchies. So you got it, right? So do you have any doubt? You can ask me. If you have any doubts in these directory structures, you can ask me. Please do ask me if you have any doubt. I can help you, right? So you understand the PDK directory structure, right? This is very important because we cannot always go to the tool and see all those things. Anyway, that's why I'm giving you that reference initially so that you will understand. Because the initial classes of ours will be this way only. I will be showing you each and everything. And after that, we will have the lab classes. So there we will do the things on the tool. And there you will get the what you say, the sense and flavor of everything. Because you will be knowing the fundamental and basics of all these things beforehand only. Okay, so you understand, right? PDK file structure, which is very important. Okay, so in the PDK file structure, we have the models folder, we have the cells folder, we have the tech file, we have the LVS file, and we have the cadence file, let's say. So in the models file, we simply have the spice files. Like in the cells file, we have the .lib file, .lef files, .gds file. In the tech file, we usually don't have .lef files, .tf file. We have the layer map file. Okay, in the layout versus schematic, or I can say that it should be in the tech file only. The PVT, we will have the DRC file, LVS file, PX file, because these are the parameters where we have to check. Okay, and in the cadence file, we will have the cds.lib file to invoke the setup. Okay, so if you have any doubt, you can ask me. Otherwise, we have completed today's lecture.
In this course, you can teach DRC how to create DRC rules.
Okay, DRC rules we are not creating. DRC rule will already be there in the PDK. Okay, so when you are, let's say, okay, you can also include your DRC rules as well, but that is always out of scope. Okay, so let's say you are creating let's say you have created a substrate. Now you are putting a gate. Okay, this is your gate. I show you that file. It was there, I guess. Let me show you. Something like that. Okay. Okay, right. Now you will place some context here. Right. Now you cannot place contact here. Yeah, I'm not able to rub it. Okay, now let me change the color.
Yeah, I'm asking. I think SVRF language is used to create DRC rules.
Can you repeat?
SVRF, there is one language, is there two
Okay,
language.
in system Verilog you are asking, is it?
Yeah,
Yeah, system Verilog we are not. System Verilog is the RTL here, at the RTL, right? After RTL, we convert
no,
that into the gate level netlist. After gate level netlist, what happens is each gate is denoted through the some NMOS, PMOS or something like that. Okay. Now these NMOS and POS at the layout and the floor planning way, all these NMOS and PMOS layer will be decoded by this type of structures. So there what happens is when you are connecting, so you cannot place your contact here because it will say the minimum spacing here should be 1 nanometer or 2 nanometer. Okay, so that those type of rules are there in the DRC. So if you are not placing this contact at the correct location, then it will flag an error. It will say this is the DRC rule. You cannot violate this because your contact is having very less or the minimum width is not meeting the requirements. So you need to change that or you need to increase this width. Okay, so those rules are there in the DRC. The DRC, there is no link between the DRC and the system Verilog code. Okay, system Verilog is the front end part. DRC is at the layout part that comes in the backend. Okay, you got it, Manohar?
yeah, but I'm not asking about system Verilog. There is standard verification uh, rule
What?
format.
Your voice is low. Can you repeat again? And
Yeah, standard verification rule format. I think SVRF.
in SV,
Yeah, SVRF.
you are talking about SVR, standard
Yeah,
verification.
rule format.
Okay, so that is a type of DRC file. DRC, is it?
Yeah, it's used to create DRC files. That is, I'm asking. You can teach that language in this course.
That language is not part of that course. This course.
Okay.
You understood this SVR? Like we usually don't create this file. Or if you have a particular profile in a company where you are working and you are doing some kind of these things. So there you will learn these things. This is not a part of something which you learn at this level. I guess this is not of that scope,
Okay.
right? Because when you are doing this like DRC and from the layout context, I'm saying, okay, these SVR sometimes some, as you said, these are some standard verification rule formats, right? Okay, so these are
Yeah.
basically when you are some EDA designer or you are some like someone who is designing the tool or who is like upgrading the tool. So there you need to take care of all those things. So I don't know, like if it in the RTL flow or at the front end and back end you are doing things, then this is useful for that. So there it is not of that useful. So at least for this point, like for this course, we will not be reading the how we are creating the SVR file. Okay, you can see the VLSI for Gate website. What will be the contents of this course? Okay, okay, you got it, Manohar?
Yeah, I got it.
Okay, okay. Thank you, guys. You can leave.